Okay, today we can see another chapter, that is thermodynamic potentials and Maxwell's equations. So, as you know, a thermodynamical state of a system can be explained or represented by the variables pressure, volume, temperature, and enthalpy. By using these four variables, a thermodynamic system of a thermodynamic state of any system can be explained. But in order to describe a thermodynamic state of a system completely, certain other relations are also to be required. These are called thermodynamic functions or thermodynamic potentials. So, every thermodynamic state of a system can be explained by four variables: pressure, volume, temperature, and entropy. But in order to describe thermodynamic state of a system thoroughly, that is completely, certain other relations are also to be required. These are called thermodynamic functions or thermodynamic potentials. These thermodynamic functions or thermodynamic potentials are energy functions. They are formulated by combining the basic thermodynamic variables, that is, as I said earlier, pressure, volume, temperature, and entropy. So, the thermodynamic functions or variables or potentials can be formulated by the basic thermodynamic variables PVTS, that is pressure, temperature, volume, and entropy. Volume and entropy. So, what are the thermodynamic potentials or functions? Let us see. The first thermodynamic potential is internal energy. This is denoted by capital U. And the second thermodynamic potential is enthalpy, or it can also represented as total heat function, denoted by capital H. The third one is Helmholtz function. This is denoted by capital F. And the fourth one is Gibbs function. This is denoted by G. These four functions are called thermodynamic potentials, and these four are formulated by combining the basic thermodynamic variables, that is P, V, T, and S. Okay, so now how the four quantities U, H, F, and G, that is internal energy, enthalpy, Helmholtz function, and Gibbs function, can be written in terms of the thermodynamic variables P, V, T, and S. Let us see. So, what is the first thermodynamic potential? So, the first one is internal energy. This is denoted by capital U. So, what is internal energy of a system? The internal energy of a system is the sum of kinetic energy and potential energy of molecules in the system. So, the internal energy of a system can be defined as the sum of kinetic energy and potential energy of molecules of the system. So, this internal energy can be explained by the first and second law of thermodynamics. As you know, what is the first law of thermodynamics? The first law of thermodynamics is dq equal to du plus dw. Here, instead of dw, we can write pdv. Why? Because, as you know, the work done dw can be written as pdv. So, from the first law of thermodynamics, we can write dq equal to du plus pdv. This is equation number 1. Now, as you know, what is the second law of thermodynamics? The second law of thermodynamics is dq equal to tds. So, this is equation number 2. So, in order to explain the internal energy, that is thermodynamic potential U, you have taken 2 equations. What are those? The first law of thermodynamics and the second law of thermodynamics. So, you see, from these 2 equations 1 and 2, you can write this equation. Suppose if you substitute the equation number 2 in the equation number 1. So, instead of dq, if you write tds, then you can get this equation. What is this equation? tds equal to du plus pdv. So, as you are explaining the internal energy, so from this equation, you can write, if you write du, this equation becomes du equal to TDS minus PdV. TDS minus PdV. This equation represents or explains the internal energy of a system. That is the thermodynamic potential internal energy of a system. So, this is the equation related to internal energy. What is that equation? du equal to TdS minus PdV. Now, if you take entropy and the volume as constants, now see how this equation can be written. Suppose if you take this entropy of the system as constant, if S is constant, what is the value of ds? This will becomes 0. So, if S is constant, then the change in entropy, the change in S will become 0. So, if you substitute this value in equation number 3, then how can this equation can be written? du equal to minus PdV. from this equation, P equal to, we can write it as dou U by dou V at S. So this is the equation. We can write minus sign here. So you see, so from equation number 3, if you take entropy as a constant, then ds will become 0. If ds is 0, from this equation, du will become minus pdv. So from this, if you take pressure, then minus P becomes dou U by dou V at S. As you taking entropy as a constant, you should read it as dou U by dou V at S. At S. Similarly, in the same manner, if you take volume of the system as a constant from this equation, then dV becomes 0. dV becomes 0. Then what is the equation you can write from this equation number 3? du equal to dds. This term will becomes 0. Now from this, t can be written as dou u by dou s at v. Why you are spelling like at v? Why? Because we are taking volume as constant. So that is why I spell at V. So T equal to dou U by dou S at V. So this is how one can explain the thermodynamic potential, internal energy with the equations, with the thermodynamic first law and second law as like this equation, du equal to TdS minus PdV. So as you know how the thermodynamic potential internal energy can be explained. The internal energy is a sum of kinetic energy and potential energy of the molecules of the system. In order to explain the internal energy, I have taken the first law of thermodynamics and the second law of thermodynamics. If I substitute the second law of thermodynamics in the first law of thermodynamics, I can write the equation TdS equal to du plus PdV. As we are explaining internal energy, so that is why I can write du, then du becomes TdS minus PdV. From this equation, if I explain this equation at the constant variables, as S is a constant, as V is a constant, if S is a constant, then ds becomes 0, then this total term will become 0. From this, minus P becomes dou U by dou V at S. Similarly, if you take V as a constant of the system, then this total term will become 0. Then T equal to dou U by dou S at V. Similarly, you can explain the remaining 3 thermodynamic potentials also. It is very easily you can explain the remaining one. Okay, so but you should remember this equation. What is this equation? du equal to tds minus ppt. This equation came from the combining of the first and second law of thermodynamics. This is a very crucial equation. du equal to the change in internal energy, du equal to tds minus pdv. Now we move on to another thermodynamic potential. What is that? Enthalpy or total heat function. Enthalpy or total heat function. This can be represented by the letter H. Okay, now we can see what is enthalpy. So this is the total heat function of a system. So that is why we can explain, we can write a relation for enthalpy as H equal to U plus PV. So as you know, what is U? This is a internal energy. This is internal energy of the system. And what is the PV? The work done of the system. work done by the system or work done on the system. So these two becomes, the sum of these two becomes, will gives us the total heat function H. So H can be written as H equal to U plus PV. Okay, so H gives the heat content, total heat content at constant pressure, the total heat function. That is why enthalpy is called as total heat function. So that is why we can represent by the equation as H equal to U plus PV. Now, differentiate this equation. What is equation number 4? What is equation number 4? H equal to U plus PV. Now, if you differentiate this equation, now what is the differential equation of this equation? dH equal to du plus PdV plus VdP. So, this the differentiation of this equation will becomes like this. So, dH equal to, so you differentiate U and you differentiate P. So now dH equal to du plus PdV plus VdP. So you know well about the how in differentiation how you can differentiate AB, A dV plus dA into B. So that like that manner, you can write dH equal to du plus PdV plus VdP. But in the previous one, you have the equation for du. So what is the equation for du? You know well about that. du equal to TdS minus PdV. So if you substitute this equation in this equation, if you substitute that in this equation, dH equal to, if you write TdS minus PdV in the place of du plus, so you can rewrite these two terms as it is, PdV plus VdP. So here you have minus PdV and we have plus PdV. These both are cancelled each other. Then what you have, what are the remaining terms you have? dH equal to TdS plus VdV. Okay, so this equation represents, explains the thermodynamic potential TH, the thermodynamic potential H. So, how we can explain the thermodynamic potential as a equation, say samikaranam dwara, through a equation, how one can explain the thermodynamic potential enthalpy dH equal to TdS plus VdP. So this is the equation related to the enthalpy. So enthalpy is a total heat function. So after that, as we have seen in the previous total internal energy, now in this equation also we can take the entropy as a constant and we can take pressure as a constant. Suppose if you take entropy as a constant, then ds becomes 0, then this total term becomes 0. So then you can get dH equal to VdP. So from that equation, V can be written as dou H by dou P at S. Why? Because you are taking the entropy as a constant. Similarly, if you take P as a constant, then the change in pressure will become 0, then the total term will become 0. Then the equation becomes dH equal to TdS. So from that, if you write the temperature, then T equal to dou H by dou S at P. Dou H by dou S at P. So from these equations, one can explain the thermodynamic potential enthalpy. So like this, we can easily explain the thermodynamic potential enthalpy. So what is enthalpy? Actually, enthalpy is the total heat function of the system. This can be explained by the equation H equal to U plus P. So you have differentiate this equation. After that, instead of du, you can write dds minus pdv. These two terms will be cancelled out. From this, you can get this equation. From this equation, if you write entropy as a constant and pressure as a constant, you can get these two equations. So, according to the situation, by using all these equations, we can easily explain a thermodynamic state of a system. Similarly, what is the thought thermodynamic potential? Helmholtz function. Helmholtz function. So, this Helmholtz function can be defined by the relation. This Helmholtz function defined by a relation F equal to U minus Ts. As you know, what is U? Total internal energy. And what is Ts here? So you are subtracting this Ts term from the internal energy term. Now what is Ts here? Here Ts represents unavailable energy in the system. So, in every system, there is some energy that is unavailable for either doing work or for transfer. This is unavailable energy exists in the system. So, this can be represented by T into S. If you substitute this unavailable energy from the internal energy, that energy gives the available energy, that is nothing but Helmholtz function. That is nothing but Helmholtz function. So that Helmholtz function, we can spell it as Helmholtz free energy. Why? Because this is the energy. This is the energy is available either for doing work or for transfer. So this Helmholtz function can be defined by the relation F equal to U minus Ts, where you know U is the internal energy and Ts is the unavailable energy. If you subtract this one from the internal energy, you can get the available energy. That is why Helmholtz function is also called as Helmholtz free energy. So from this equation, from this relation, you can get, you see, if you take F equal to U minus Ts. Now, if you differentiate this equation, so you see, if you differentiate df, F, you can get df. If you differentiate u, you can get du. If you differentiate ts, so what we get? Minus tds minus sdt. So, as you know, as usually, you can substitute the value of du in this equation. So, what is the value of du? tds minus pdv. So, again, we can write this terms as it is, minus tds minus sdt. So, we can cancel these two terms. What are those terms? tds minus tds. So, just we have df equal to minus pdv minus sdt. So, this is the relation. This is the relation with which we can explain the Helmholtz function or Helmholtz free energy. So, as usual, like in previous one in thermodynamic potentials like total internal energy and enthalpy, from this equation, if you take volume as a constant, if you take temperature as a constant, so what will happen, you see, if you take volume as a constant of the system, then dV becomes 0 and this total term will become 0. Then dF equal to minus ST. From that, minus S equal to dou F by dou T at V. Similarly, if you take temperature as a constant, then the change in temperature will become 0. Then this total term will become 0. From that, you can get Tf equal to minus Pdv. Then minus P equal to dou F by dou V at T. So this is how we can explain the Helmholtz function or Helmholtz free energy. So Helmholtz function can be defined by the relation F equal to U minus Ts. This Ts is unavailable energy in every system. Either it is not usually either for doing work or for transfer. So if you subtract this one from the internal energy, then you can get the available energy of the system. That is why this Helmholtz function can be called as Helmholtz free energy. Now the fourth one, the thermodynamic potential energy is Gibbs function. So what is Gibbs function? Simply, this Gibbs function can be defined by the relation G equal to H minus Ts. As you know from the previous topic, this Ts represents unavailable energy in the system. If you subtract this unavailable energy from the total heat function or enthalpy, that gives us the energy function G. That gives us the energy function G. Therefore, if you differentiate this equation, dC equal to dH, and we can write it as minus TdS minus STT. Instead of dH, if you write, as you know, what is the value of dH? dH is TdS plus VdP. So instead of dH, if you write TdS plus VdP minus TdS and minus SDT. So what will happen here? This TdS and this TdS minus TdS will be cancelled out, and you can get dZ equal to VdP minus SDT. So this equation explains the thermodynamic potential Gibbs function. Gibbs function, this can be represented by or denoted by G. So from this equation, if you take pressure as a constant, then dP becomes 0, then VdP becomes 0, then dZ equal to minus SDT. From this, minus S equal to dou G by dou T at P. Similarly, if you take temperature as a constant, then dt equal to 0, dt becomes 0, then minus SDT becomes 0, then dZ equal to VdP. From that, P equal to dou Z by dou P at T. So this is how these equations can explain the Gibbs function or thermodynamic state of the system. So like this, we have 4 thermodynamic variables and 4 thermodynamic potentials. So in order to explain the total thermodynamic state of a system, we need 4 thermodynamic variables, along with we need for 4 thermodynamic potentials. These 4 thermodynamic potentials are formulated with the basic combination of these 4 thermodynamic variables.